Well, hello everyone, and welcome back to P34, last tab. So this is very similar to the previous tab. It's going to be a two-sample t-test, assuming unequal variances. A software development company wants to determine if a new user interface reduces the average time it takes to complete a specific task compared to the old UI design. To investigate, the company randomly selected users and presented them with new and old UIs. Their completion times were recorded. At the 0.05 significance level, can the company conclude that the new UI design reduces the average task completion time, assuming the population variances are unknown and unequal? So the case here is one tail left because it reduces, and the distribution is t because we do not have the population standard deviation. So then let's go ahead and count number of records in each sample. These are again small samples. And the only downside to small samples is that your difference has to be even that much bigger before it will be tested as statistically significant. So now we have the count, mean, and standard deviation of all of them. Let's see what the difference is. Is the new one minus the old one? Okay, I mean, it looks like a pretty big difference compared to the size of those numbers, but let's see if it holds up. So the null hypothesis is no significant difference, and the alternative is that it's going to be less than. The population mean for the new UI is going to be less than the old. Expected mean difference is 0. And then here's our expected variability, square root of s squared divided by n plus s squared divided by n. And that's our expected variability. So that's not a lot of expected variability, and we had a big difference. So this one might be significant. Let's see, alpha is 5%. Degrees of freedom, remember, you can see the calculation if you want to, but we're giving that to you. And then the critical value lower bound is going to be equal to t dot dist t dot dist, sorry. Not t dot dist, t dot inverse. And I keep forgetting if there is well, I think it's fine. T dot inverse, the probability t dot inverse dot 2t, sorry. Probability, degrees of freedom. And remember, that gives us the wrong one, so we'll make that a negative. And then do the same thing. T dot inverse dot 2t. Probability, degrees of freedom. And then we'll do the one tail left, because it actually is a one tail left test, so it's going to be t dot inverse probability. See, notice there isn't a t dot inverse dot lt for left, because left is the assumed degrees of freedom. Okay. So what's our t-score? Observed difference divided by standard error is negative 11. What's the probability of seeing negative 11? I mean, that's huge for a t-score, so that's probably going to be a really small probability. Remember, anything bigger than 3 terms of standard deviations, as you know from the empirical rule, is way out in the tail. In fact, you can see it over here, right? I mean, we're way out in the tail. Here's the distribution, and we're like out here. So that is not only a reject, that's like emphatically reject, because we are like way out in the tail over here. Let's see if we can calculate that probability, which looks like it's basically 0%. So that equals t dot dist x comma degrees of freedom, and true for cumulative. So yeah, it's basically is basically a 0% chance. I mean, obviously there's a tiny fraction in there if we extended all the decimal places, but it's basically saying there's a 0% chance that that you would observe a difference that big if the expected variability was that small. And so the conclusion is that you reject the null. The reason is that 0% chance of observing those sample means. That means the samples probably come from different populations. So if they come from different populations, we are saying that the new UI does reduce time. So it significantly reduces time from the old. But if we're wrong, it would be a type 1 error, rejecting the null when it's actually true. All right, so if we are, then all of a sudden this becomes much more interesting, the confidence interval, because that'll tell us where the real population mean is for the new UI. So let's grab the difference, starting difference, and subtract from that minus the two-tailed positive times the standard error, and that equals that plus the two-tailed positive times standard error. All right, and if we look at it on the graph, what we're effectively saying is that not only is it less, right, with a new UI, but the true value in which it's less, it's going to be a savings of between 6 seconds and 10 seconds less. That's the true value for the population. And notice that we're getting all that, we're inferring all that. That's why it's called inferential statistics, because we're inferring all that from the sample data, which is really cool if you think about it. And that's it for Prep 3-4.